Okay, so good morning, and today we will continue our introduction or a prelude to special theory of relativity. And so last lecture we argued that that in a moving frame, okay, an electric field must appear even though there was none in the initial frame, in the first frame. Right, this was we called A in frame A, and I'm what I'm calling moving frame. Okay, so we needed this so that there would be no force, right? So this is what we got, and then so this was the argument was something like this, and so we were looking, we wrote out a general form of how an electromagnetic field in frame A will appear. All frames are inertial frames, okay, mutually inertial. Frame A will appear in frame B. Okay, so, and we use primed for B and unprimed for this thing. So we wanted a formula of which will express the electric field as a function of u, e, and x. Okay, remember that nowhere we have said that the electric field E and B are are constant or homogeneous. Okay, they're all functions of x and t, and so E prime will be this will be naturally a function of x prime and t prime, and E and B will naturally be a function of x and t, of course, because in frame B you will not work with coordinates in frame A, right? Obviously, anybody will work in their own coordinate systems, but we are putting in this fact that that it can depend on the velocity u. Okay, that's the relative velocity between the two frames, and then I argued based on general. There was some argument, right? What happens when u equal to 0? Okay, so now in all these things, E is a function of x and t, while E prime is a function of x prime and t prime. I'm not going to write that because formulae become too messy. Okay, and then using the fact that E was a polar vector, we saw that we could only add a term of this thing to order u. And similarly, B is an axial vector. So there wasn't much we could do. Okay, so is this statement clear to everybody? That
yes, sir.
Okay, and that cannot be, this A1, A2 cannot be functions of x and t or anything. They are just some constants. They are some numbers. Okay, so all the x and t dependence and x prime t prime dependence are buried in the functional dependence on E and E prime. So it's fairly strong statement. Okay, and let us so we go back to our first our first thought experiment. Okay, sometimes people use the German word for this. It's called, I think, Gedanken experiment. Okay, that's the German for thought. Okay, so we want to fix E1. So our first thought experiment, we saw that we work with E equal to 0 and some B was non-zero, and we saw that we needed what was the thing we needed? Electric field should be something like this. We won't worry about order u square, so I'm just putting that. Is that what we wanted? So let's remember, particle with charge q will be moving with velocity minus u. So the induced thing should be plus u, plus 1, right? Okay. So in this setup, that corresponds to putting this E equal to 0, and this will become 0. So what it says is B prime will be B to order u square. So this term is fine. But so what should A1 be for this to work? This thing rather goes to, from A. This is in frame A, and this is in B. So what value of A1 will achieve this?
1.
Okay. So just comparing, we see that A1 should be equal to 1. And we can't fix A2 with this thought experiment. Why? Because E is 0, so the U cross E becomes 0, so we can't fix, okay. Okay, so now the question is, how do you fix? So we will do, so we will next fix okay. So again we will work with we use the same charge. Q, but we treat it as a source. Okay, so in frame A, there is E is not 0 and B is 0, right? A point charge, and which is, let's say, located at the origin or at R prime or something like that. Okay, so, and what is E? So in frame A, we can be even more concrete. E is K, Q, R by R. Okay, so charge at origin. For simplicity only. Okay, so this is what we get. Okay, so now we can so what does frame B see? Okay, so frame B, we have a charge moving with velocity. What is its velocity?
Minus u.
Minus u. Okay, and its instantaneous location is R prime equal to, it's at the origin in R, so it will be just minus u times t prime. Is this clear? Okay. Okay. So one thing we know is that Biot-Savart's law or Biot-Savart law tells us that there will be a magnetic field, right? A moving charge or a changing current, etc., right? That there will be a B field. Okay, so, and if you remember, there is something like this. B at some location R, oh, now it is messy, but okay, at some location R and, okay, is given by mu naught by 4 pi. Hopefully you remember this formula. IdL for a charge element, you integrate over the loop or whatever, cross the location. dl prime, and this is r prime, and we're interested at the location r. Okay, so this is what we get. And r prime is minus ut prime or whatever, doesn't matter. So for...
Excuse me, sir.
Yeah.
Yes, sir, can you just go back a little and explain how you wrote the electric field in U frame as U cross B? Just a little ago.
U cross T?
U cross B.
Oh, this one.
Yeah, okay. We figured out A1 is 1, right? So
okay. So how did I write? I mean, I didn't use that experiment to write this. I said that, the facts, we use some data, right? First thing is that when U is 0, okay, E prime should be E. So that fixes this term. So it's plus order U. So we're asking now, what are the terms which will be linear? One, I should use one U. I can use E and B. I'm allowed to use any combination, but I should create a new vector from that. Okay. So the only vectors I can create, which is one U and either B or E, is U cross E and U cross B.
Yes, sir, I understood that part, but
yeah.
Below this 0 comma B goes to another frame U cross B comma B.
Yeah. So I'm just plugging in. I'm putting E equal to 0 and B, keeping B non-zero. That's our setup, no? That's a special case. So in our
frame, the U frame, electric field is U cross B.
Is purely U cross B. 0 plus U cross B. Because E is 0, right? In our thought experiment, E is 0. Right?
Yes, sir. I mean, force will be Q into V cross B. So are we assuming?
Yeah, so we wanted the total force to cancel.
Oh, okay.
Right? So the Lorentz, the magnetic field force, we said is okay, we'll approximate it by, we said U will be so small that we can make U as small as possible, okay? Yes, but there will still be a force which is minus U cross B.
Yeah.
Minus because that's all.
Yeah.
So to cancel that, the electric field better be U cross B.
Yes.
That's all. And this big O is very useful, you see now. It tells us we are neglecting, we are not even worrying Lorentz force law, maybe it will get corrections of order U square. We don't know that, right? I mean, we'll just say something. So we don't know all those things. So, but at least to this much order, we are sure. We know that, U cross B has been tested. Q into V cross B, that part has been tested very well. So that takes care of it. And that's how A1 becomes 1. Is that clear? Okay. Yes. Thanks for asking, because these are small details. So now what I'm going to do is do a different setup where E is non-zero, but B is 0 in frame A, and then ask what we get. Okay. So this is for a loop, but hopefully you know these replacements, that IDL gets replaced by QV, Q times velocity for a charge, for a moving charge, with velocity EV. Okay, and the velocity for us is minus U. So what we get is B prime actually. And this is the prime fellow because we are working in frame B. B prime is mu naught.
Sir, isn't there a cube R minus R prime cubed? in the integral.
Yeah. Sorry, I got interrupted, I think, so I didn't write it. Doesn't matter. Anyway, I keep dropping things. Minus u cross, okay, q at the location r prime. Again, I forgot the q. Okay, so this is what we get. Okay, so now what we have to do is what I'll do now is multiply and this thing by epsilon naught, etc., and I write this as mu naught epsilon naught into minus u cross, put something in square brackets. We've been working in okay, but now comes the fun part, is that this thing is what is this object in square brackets? It's E plus order u square, right? It's the electric field due to the thing, and r prime, if you remember, was in frame A. It is the origin. It is like shifted, so it is doing this. So what I want to claim is that this is equal to E, and there could be terms order u square which I'm messing up, which I don't care about at this point. Is this clear? Okay. And we know one more thing. We know that mu naught epsilon naught is 1 by c square. So I'll collect all these things and we will see it is 1 by c square into minus u cross e. Okay? Do you agree with this? What I'm saying is E prime, already there's a U here. We know E prime would be, there might be corrections to E prime of the order of U, but U into U is U square, so we are not interested in that. So to that order, so we are interested only to order 0. At order 0, E prime is E. We know that also. That's all I'm doing. Okay, so what is A2 now? Now we can compare, right? So now you can see that it's fairly non-trivial that I was able to rewrite whatever this thing for this experiment. But of course, it could be true for any experiment. Okay, but we just need to do 2 simple experiments. So what does this imply for A2? So we just go back and compare. So it said A2 should be some A2 times U cross E. And what did we get? 0 plus something. So the A2 will be do you agree with this? Okay, so our experiments will help us fix these constants, but the general form is given on very, very general considerations. There's nothing, no deep thing. Is this okay? Is anybody having trouble with this? So we go back to this thing.
Sir,
Yeah.
the R vector we are using in the expression of electric field.
Yeah.
And the R vector we are using in the expression of B dash vector from the Biot-Savart law. These are different, right?
Yeah, exactly. But the difference will be will give you terms of order u square. That is the point. I'm not interested in corrections. See, R prime is ut. We are not interested even in what t is. What I'm saying is order u. R prime is order u.
I mean, we wrote the same vector, R vector, in the expression of electric field.
No, all this is in this expression here, which I'm marking right now, is not in, it's in frame B. It's just a computer. Until this point, there is no approximation. Until this line, actually. But now when I do this, so this would be, this is like E prime in some sense.
Okay.
Right?
Okay, sir.
If I had called it E prime, you would not object. I'm saying, but E prime is E plus order U square. So I jumped one step. You're right.
Okay.
Correct?
Okay, sir. Thank
Okay,
you.
great. So we have a nice, beautiful conclusion. E prime equal to E plus U cross P plus order U square, and B prime Is this fine? So this is just a conclusion. So we fixed the constants by doing two experiments, but you are welcome to try other experiments, and you will still. I mean, because the thing considerations are so general, it doesn't depend on our experiment. We just did two. It was easier to use one. I mean, these two situations, but we could do a much more complicated situation where we handle E and B simultaneously. Okay, we could have done that. But superposition tells you can do these two cases and then add them together, and it should work. Okay. Okay. So the conclusion is this, and what does it mean? It says that E and B mix with each other. As we go from one inertial frame to another. That's all it says. And it says it gives you in a much more stronger form. It tells you how it is to order U. And the biggest point takeaway here is that we did not make the assumption that U has to be large. Okay, U can be as small as you want, so that we can, all these order U square terms can be forgotten about, or we can work. I mean, so this we cannot rule out. And the key point here is that Lorentz law has been tested, right? At least to order U, we know that our Lorentz law is corrected. And and again, Biot-Savart's law, etc. All these laws are at least true for slowly varying fields, time varying is variation slow, everything we know those things. But of course, Maxwell's equations, there is no assumption like that when you write Maxwell's equations. But all these other equations which we learned, integral equations of the kind that we learned in high school, they are of that variety. Okay, so this is where our sophistication comes in the fact that we are now, we understand big O and things like that. Okay.
Sir, this order of U square is getting further divided by C squared, so it will be really very small, right?
Yeah. No. We have now it's a little bit ugly in the sense that there is some ugliness, and we'll make it better. Okay, and this ugliness has to do with the fact that E and B are measured differently. You can see that E by B has dimensions of U of a velocity. Okay. So once we'll just go to Gaussian units. In Gaussian units, it will become exactly that. Okay. It's a little bit ugly to say something is order U square. Because U is a dimensionful quantity. So what does that mean? To be large or small? It would be nice if it were dimensionless. Okay. And we will do that, and we'll go to Gaussian units. That's what we're going to do next. And we will see that wherever we saw all the C squares will go away and all the U's will become U by C's. And then it's exactly what you're saying.
Yes, sir.
Okay. It's not yet. It's right. You agree? It's pretty ugly the way we have done it, but it's okay. Okay. So that's what I want to discuss next. Okay. So the problem with the above formula is that in SI units, E and B are measured differently. Okay, just say that suppose we were looking at some displacement vector, and for some weird reason we decided to measure x component in centimeters, y component in meters, and z component in kilometers. Okay, then if you're but we know under rotations things mix, but now we have to remember that we are measuring x, y, and z in different components, and there'll be these ugly. So, for instance, going from centimeter to meter, there's a factor of 100. Going from meter to kilometer, there's a factor of 1,000. These are all known there'll be some well-known constants, so it doesn't really matter. Okay, but it makes writing rotation matrices ugly, right? If you measure x, y, and z components in different units. Okay, so this is what is happening here. Here we are seeing E and B mix, except they are mixing, they have different units, and that's where we start seeing all this. And you can see that the factor that is coming is C. Okay, it's a velocity factor because that is the ratio of E and B is a velocity, has dimensions of velocity or speed. Is that clear? So solution is to go to units where E and B are measured identically or in same units. Okay, and that's what we will do. So we go to Gaussian units. So we go to Gaussian units where this is true. Okay. So I'll give you a thumb rule how to convert. Okay. Okay. Gaussian units from SI. There are some small things. The first rule. So I'll give you some rules. First rule is set 1 by 4 pi epsilon naught should go to 1. Okay. So the correct statement is that Coulomb's law. Okay. The magnitude of, say, the forces between two charges is Q1, Q2 by 4 pi epsilon naught R12 square. This is SI. Okay. But in Gaussian units, okay, F is okay. Q is measured in coulombs here. Okay, here Q is measured. Anybody know the unit? In stat coulombs. Okay. So that just means wherever you see epsilon naught, put 1 by 4 pi, right? So thumb rule. So of course Q has to be written coulombs becoming stat coulombs. I'm assuming that, but for equations, okay. So equivalently, so set epsilon naught equal to 1 by 4 pi in ME. This is what you need to do. Okay. So this is the first change. The second one, replace B, wherever you see B, by B by C. Okay. So this is what you have to do. These are the two changes. Okay. So if you want more on units, so I'll give a reference. of the classic book on electrodynamics by Jackson, which is a very tough book, but I'm only asking you on units. You'll be surprised how many units are there. He's got tables, how to go back from it. Okay. All of you have heard of Jackson, right?
Yes, sir.
Yeah. It's one of the most, it's actually a beautiful book, but it's also a very difficult book. And but it's a standard book in most PhD programs when you're doing electrodynamics. You do that and you do, typically you do that whole book in one full year. Okay. So in these units, the mixing is simple. Okay. So now you can see my claim work out, which is that, oh, okay. Am I at the border of a page? I don't know why it's not working. Okay. So is this clear? And now you can see that in Gaussian units, E and B are measured in this thing. So whatever is this factor, U by C is dimensionless. Okay. So I have an exercise now. Show that ME, Maxwell's equations, in Gaussian units. Okay, this should take you exactly a minute if you can just follow the rules. That's all I'm saying. Nothing happens here, dividing by C or whatever, it doesn't matter. Okay, now comes C. Nice thing. This is what you get. Okay, just some observations here. So the del operator has dimensions of inverse length. D by dt has inverse time, but 1 by C d by dt has dimensions of inverse length. So you can see that once E and B, so all the, what was so in SI units, there was one more feature. Mu naught and epsilon net came in various places. Okay. What is happening here is that we are seeing that mu naught and epsilon naught disappear, and it shows that Maxwell's equations has only one free parameter, which is C. Okay. Okay, and then we can identify this with the speed of light, because if you write out the wave equation, which you can get from look at source-free Maxwell's equations and obtain the wave equation, you will see that the waves, electromagnetic waves, the C becomes the speed of propagation of that electromagnetic wave. So and there is this huge identification that light is an electromagnetic wave. So there are many steps we have got to do. But at the level of the way we are looking at Maxwell's equations here, C is just a parameter. But then we can look at this special class of solutions, which are like plane waves or whatever. You'll see that these waves propagate with this speed C. Is this point clear?
Yes, sir.
Okay, and it's important to realize that C is just Maxwell's equation doesn't tell you what the value of C is, and it is not even relevant if you think about it. Okay, all that is relevant in this story is that C is some non-zero number, because it can be large in some units, it can be small in some other units, right? So if I'm going to measure distances in light years, okay, then C would be if distance is measured in light years, what is C then in that?
It will be very less.
Yeah, it'll be 1 year. I mean, so distance by time, right? So yeah, so you can see how it will change. Okay, so you just go ahead. It'll be 1 or something in some units, right? 1 whatever, right? Okay, so this is something which you should kind of take it. Okay, so while that's a word which is used in theoretical physics, which is that as Gaussian units. Is natural. For SR. What one means by that is that SR becomes, it becomes manifest, right? I mean, like I said, rotation. If you want to write rotation symmetries, etc., if you want to write Newton's equations with rotation symmetries, and if you measure different units in X, Y, and Z, it will be very ugly to write. The vector notation can't be used, right? So similar things happen here. We will see that there will be an analog of vector notation which comes for this, and we will be able to rewrite Maxwell's equations in a way where special relativity will be manifest. Okay, so there's one more observation that we can do. Observations, if you wish, to do this computation. Okay, so what is saying is that if you remember, E prime and B prime have terms of order U, but it is such that that they cancel. The order U terms cancel. So that is the key thing. Okay, this is easy to check, but the remark which I want to make is actually these identities hold to all. We are not proving it yet. Okay, all orders in U. This is non-trivial. Okay, so now the point is, now we should ask implications of the mixing that we obtained. So, okay, so this is what we want to ask, and so what we will do before that. So we will do this in 2 steps. Yes, actually, okay, but first, by asking how the scalar and vector potentials transform. Okay, hopefully you remember that E of x and t would be minus gradient of phi of x and t minus dA by dt. Okay, and in Gaussian units I need to put a 1 by c. Okay, so I'll write it in Gaussian units, and B of x and t would be del cross A and x and t. So we know how, so similar things would be there in frame B also. Okay, so we will need to work it out. A prime and phi prime can be written so we can write some general things again. We could say something like A prime should be a function of u, it should be a function of A and phi alone. Same kind of story. And similarly, phi prime should be a function of u, A and phi. Okay, but now we need to work out these things. We need to ask what are these? How do they look? Okay. This is what we want to work out. Okay. So one thing we want to know, which we already have known, is how are the coordinates related? Okay, and that we think we know, right? X prime must be x and minus ut. Okay, and we would like to write t prime equal to t. Okay, and now what we will do is we'll be very, very careful. Maybe there are corrections to this at order u square. We don't know. We could. We might have. We don't know that. Okay. Again, we don't want to be biased in any form, so I'm playing it safe. Okay. It could be true that there is no order u square term. Like I wrote here also, right? We wrote something here that there is at order u square and order u square terms here. But my point is that there could be zero. Like I mentioned, there happened to be. We'll show later that it is zero. Okay. So t prime can be equal to t. Okay. Now, so far this is what a Galilean boost would have said. There is no corrections at order u square. T prime, if I match the times, t prime is equal to t. Okay. We're going to assume that. Okay.
Sir, if there was u square, then they would not be mutually inertial, right?
No, we don't know that. We don't know that. Okay, what I'm saying is that if you are going to for Galilean boosts, there is no such thing. That's all I'm saying. Whatever I've written right now is true for Galilean boosts to all orders in U. Correct?
Okay.
Okay. But now what I'm going to do here is to add one more term, which is not there in Galilean boost, but it's order U. I want to construct a scalar which comes. So I'll write that. And I want it to be linear in X for whatever reason. Don't worry about that at this point. Okay, so all the terms in yellow do not exist in Galilean boosts. Okay. A3 equal to 0 and there are no corrections at higher orders. Okay. So what we are going to do is, see, the reason I need how the space field transform is because the operators del is coming, d by dt is coming, while the guy in frame B will use del prime, Laplacian, so not Nabla or del operator in prime coordinates and in time in his coordinates, his or her coordinate systems, right? So we don't know these things. So I just want to be general and ask. We would like to think that A3 should be 0. If our calculations show that A3 is 0, that is good, no? Then it says Galilean boosts work at least to this order. Maybe a higher order terms it doesn't work. Okay, so this is what we don't know the answer. We cannot a priori assume this. Okay, so we will see in the next lecture that the mixing of E and B needs A3 not equal to 0. Okay, so this is what happens. Okay, so now once I say that even though this is an ugly calculation but straightforward, which we will do next lecture, what I'm saying here is that the term which I wrote here in yellow, A3 with a constant A3 out there, it turns out that that guy is non-zero. Okay, so obviously Galilean boosts don't hold for Maxwell's equations. But I mean, here's the thing, right? I mean, in some ways, the frames are just like some, a stage for a play, right? So, so we are looking at properties of the stage in some sense, and that shouldn't depend on what we are doing. It shouldn't be like if I run, Ramayana runs, it's the stage changes for Mahabharata or something. I mean, the stage is the stage, right? So it's like that. It's a frame. It's just some passive thing. Okay. So it shouldn't, it is going to, you're going to do one thing for Newton's equations and mechanics, another thing for electromagnetism, that cannot be correct. Okay, so the point here is that A3, once a calculation shows that A3 is non-zero, says that we don't need experiments. If you want to force A3 to be 0 in electromagnetism, that will require us to make modifications like, maybe, we have to, the Lorentz force law should change. But that we have tested to order U. We are very conservative. We are not looking at order U square terms. Okay, but suppose we got lucky. It just happened that A3 equal to 0, this thing. We still need to check at order U square what happens. Okay, to see if Maxwell's equations and Newton's equations have the same symmetries. Is this point clear? Okay. But at order U itself, it runs into trouble. So we don't need new experiments. The experiments which Faraday et al. Did is good enough for us. Faraday, Lorentz, from those areas, from 200, even before Maxwell, those are good enough. Because we are looking at effects of the kind Faraday studied, right? He only said moving charge, you do this, you get, induces magnetic field and stuff like that, right? So this is the crux of why there is a conflict between Maxwell's equations and Newton's equations in mechanics. Okay, and what I'm trying to tell you is A3 being non-zero forces us. We don't need new experiments. It forces us to modify Maxwell's equations in mechanics, and this is something which we will do after we finish this story. We will see how mechanics can be reformulated such that this non-zero value of A3 works, and it gives corrections. So what we will see is that there will be corrections which would show up in mechanics, which can be checked. Okay, and we will do some checks and balances, but you can look around and ask, what are all the experiments people have done. Maybe I will also give some results. Okay, so I'll stop here. I'm done for today and pause for questions. By the way, all this presentation is entirely mine, in the sense that I haven't looked anywhere or something. I just thought that I was supposed to teach some second year students special relativity, and I said, okay, let me try this. Will it work? And it worked. And so I've been able to refine it over the years. And okay. So any questions? Okay, I'm stopping recording. So if you're very shy,